In this video, we're going to talk about conditional probability and independence. When you are looking for the probability of an event happening, while you also know that another event has happened. So for example, let's say you pick a card out of a deck and you know that it happens to be red. Let's say you want to find the probability that that card that you know is red is also a jack, for example. So we call that a conditional probability. When you're looking for the probability of something happening when you know a condition or given a condition has already happened, that will affect the probability of what you're trying to find. Like, is this red card a jack that I pulled from the deck? So here's how we denote it using our probability language or algebra. So the probability of you looking for A, is that card a jack? Given that you know the probability of B, that it is a red card. So the probability you know is that you pulled a red card. And the probability you're looking for is that red card a jack? So you first find the probability of both A and B happening. Is it a red jack? And these two different things say the same. So 3 different ways of thinking about it. So it's the intersection, or that both events are occurring, that it is red and it is a jack. And you divide it by the probability of the thing that you already knew to be true. So that is the probability that it's a red card, probability that the given event occurs. So let's do a quick example with the Facebook versus Instagram use of residents of a large apartment complex. So remember that 68% use Facebook, 28% use Instagram, and 25% use both. So suppose we select a resident at random. Here's what we know. Given that the person uses Facebook, so that language there, given that, is usually a tip-off that it is conditional probability. Anyway, given that the person uses Facebook, so that's the thing we know, that's our B, what's the probability that they use Instagram? So that is the thing we're trying to find. So the probability that this Facebook user is also an Instagram user, right? We do A and B, so the probability that they are both, which is 25%. And then we divide it by the thing that we know, this second part here, or P of B, P of F, P of Facebook, probability of using Facebook, that is. And that's 68%. So that divided by that is about 36.8% that this random resident uses Instagram knowing that they also use Facebook. Conditional probability. So now let's switch gears from events that kind of rely on one another or related in some way to ones that are not at all. So if we have two events, let's say A and B, and if knowing the probability that one happened, so if you know the probability that event A happened, and it has no bearing and no impact on knowing whether or not the event B has happened, those are called independent events. And you can prove them using these two proof equations in a word or phrase. But let's work through an example to hopefully make some sense of this. So this one is called gender and handedness. Fair warning, they're both binaries, just male and female and right and left-handed. Sorry. But here's what we know. Is there a relationship between gender and handedness? To find out, we use Census at Schools, random data selector, to choose an SRS of 100 Australian high school students who completed a survey. The two-way table summarizes the relationship between gender and dominant hand for those students. Suppose we choose one of the students in the sample at random. Are the events male and left-handed independent? So let's do a little bit of work to figure that out. One way to look at this question is, if I know that the student chosen at random is male, is it more or less likely that that male identifying student would be left-handed? You might think, well, that has nothing to do with anything. Here's how we can test that. Let's find the probability that we have a left-handed student that is male. So I'm going to look at the male students. There's a total of 46, and the left-handed students are 7 out of 46, so that's about a 15.2% probability of a student chosen at random being male and left-handed. Now, let's say that we knew on the contrast to that the student is not male but is female. So what are the odds, or what's the probability that this randomly chosen student is female and left-handed? So all of the females are 54, and the left-handed females are 3 out of 54. Now, that ends up with about a 5.6% chance that that random student is a female that is left-handed. Now, these two things are not the same. 5% and 5% are not the same probability. But if they were the same, they would be independent, because it wouldn't matter if you're male or female. You'd have the same odds of being left-handed or choosing a left-handed student at random. But because these probabilities are not equal, the events male and left-handed are not independent. They are conditional. So knowing that the student is male increases the probability that they are left-handed, versus knowing if the student is female, that would decrease the probability that they are left-handed, because left-handed males happen more in this survey than left-handed females. Suppose you want to find the probability that two events A and B, for example, occur together. So maybe you already have that information. Maybe you already have the intersection, so you could just take that information. Another way is if you have the conditional probability of the relationship between B happening based on A already happening, you would multiply that, remember this thing, by the probability of A happening. But interestingly, this would cancel with this thing on the bottom. Weird how that works. Or not weird at all. Let's put this into context of an example. Let's talk about teens and social media. Woo! All right, the Pew Internet and American Life Project reported that 79% of teenagers, so ages 13 to 17, so not all teenagers, but they use social media. And 39% of teens who use social media feel pressure to post content that will be popular and get lots of likes and comments. Woo! The internet. Find the probability that a randomly selected teen uses social media and feels pressure to post content that will be popular and get lots of likes or comments. So that's event A, which is you use social media, or a teen that uses social media, and they feel that pressure to post content that will be popular, and blah, 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 blah. So let's figure out what that would be algebraically. So I'm sure you're not entirely surprised, based on just the name of this rule alone, the general multiplication rule, is that you take these two known quantities, so 79% of teenagers that use social media, and the 39% of those 79% that feel that pressure. Even if you just know that of in mathematics typically means to multiply, you're going to multiply those two quantities together. So 39% of 79% will give you 30.8% of teens who use social media also feel that pressure to post positive things. And now you may or may not be wondering, now what about a multiplication rule, but for independent events? So that, when A and B are independent events, they don't care about each other, they don't impact each other, they are not conditional. When you want the probability of an independent event A and an independent event B happening, you just multiply their probabilities together. This only applies to independent events. Now let's try out an example. This one's about rapid HIV testing. So many people who visit clinics to be tested for HIV don't come back to learn their results. Clinics now use a rapid HIV test that can give the results while the client waits. In a clinic in Malawi, for example, they use rapid tests, and it has increased the percentage of clients who learn their test results from 69% to over 99%. The trade-off for fast results is that rapid tests are less accurate than slower lab tests. Applied to people who have no HIV antibodies, one rapid test has a probability of about 0.004, so less than 1%, of producing a false positive, and that is falsely indicating that antibodies are present when they're not. So if a clinic tests 200 randomly selected people who are free of HIV antibodies, what is the probability that at least one false positive will occur? So assume that the test results for different individuals are independent. So using what we know, that 0.004 of the time, a false positive is produced, which is you don't actually have the HIV antibodies and you test positive for them, false positive. So what we could do is, I want to know the probability of no false positives, which is also saying that all 200 tests come back negative. So 1 minus 0.004 is 0.996. And so if they're independent events, we just multiply them, right? A times B times C, and they're all going to be 0.996. You do that 200 times, which is that number, 0.996 to the 200 power, and that is 0.4486. So about 45% of the time, no false positives, at least in this 200 test example. So I'm looking for the probability that at least one false positive will occur. So if we know that the probability of no false positives in this 200 group of folks is this number, the opposite, or the probability of at least one false positive, is going to be 1 minus that quantity, so about 0.5514. So the probability that any individual test result is negative is about 55-ish%. One last little warning about the multiplication rule for independent events. Make sure to use that wisely. Resist the temptation to use these simple rules when the conditions that justify them are not met. What am I talking about? Here's another example. Watch the weather. Beware lack of independence. So, Hacienda Heights and La Puente, apologies for butchering that, are two neighboring suburbs in the LA area. According to the local newspaper, there's a 50% chance of rain tomorrow in Hacienda Heights and a 50% chance of rain in La Puente. Does this mean that there is a 0.5 times 0.5 or 0.25, 25% probability that it will rain in both cities tomorrow? Shouldn't shock you that the answer is nope. And I don't think you need to know a lot of statistics or probability to answer that one. But just to be clear, it's not appropriate to multiply the two probabilities because raining tomorrow in Hacienda Heights and raining tomorrow in La Puente are not independent events. If it is raining in one of those locations, it's likely raining in another because they are suburbs of the same city. So, because they're geographically close to one another, they are not independent events, so you can't just multiply their probabilities together to get the probability for both. Something that might be helpful to organize multiple events that happen, especially if they are conditional events, is something that we call a tree diagram. Now, I'm sure you've seen a tree diagram before, and you've probably drawn some in the past. But as a reminder, a tree diagram shows the sample space, so everything that could possibly happen, of a chance process involving multiple stages or events. The probability of each outcome is shown on the corresponding branch of the tree, and all probabilities after the first stage are conditional probabilities. So, for example, this scenario is about a student who hits the snooze button on their alarm. So they hit the snooze button 60% of the time, so that means 40% of the time they don't hit the snooze button. And then after they hit the snooze button, conditionally, so what would happen after that? They're either on time, 70% of the time, of the 60% that they hit the snooze button, and 30% they're late when they hit the snooze button. When they don't, 90% of the time they're on time, and 10% of the time, if they don't hit the snooze button, they are late. So this is one beautiful way to organize a lot of events, especially if there are many things that are conditional upon their previous events. Let's check out an example where we use both tree diagrams and conditional probability. Let's talk about mammograms. Many women choose to have annual mammograms to screen for breast cancer after age 40. A mammogram isn't foolproof, much like many medical tests. Sometimes the test suggests that a woman has breast cancer when she really doesn't, which is a false positive. Other times, the test says that a woman doesn't have breast cancer when she actually does, which is a false negative. Also, women are not the only humans that get mammograms, just putting that out there. Suppose that we know the following information about breast cancer and mammograms in a particular population. 1% of the women aged 40 or over in this population have breast cancer. For women who have breast cancer, so of those 1%, the probability of a negative mammogram is 3%. For women who don't have breast cancer, the probability of a positive mammogram is 6%. So, a randomly selected woman, age 40 or over, from this population tests positive for breast cancer in a mammogram. Let's find the probability that she actually has breast cancer. So what I'm going to do here is I'm going to make a tree diagram with what I know. So the first two offshoots here, the first event that can happen is either you have breast cancer within this population or you do not. So 1%, 0.01, has breast cancer. That means 99%. The rest of them, 0.99, do not. And then from there, they can have a positive mammogram or a negative mammogram. So both has and does not have breast cancer have both outcomes that are conditional. We know that for the women who do have breast cancer, a negative mammogram is a 3% likelihood. So 0.03 goes to negative mammogram, 0.97 goes to positive. And then of those who don't have breast cancer, a positive mammogram is 6% likely. So that means 94% has a negative mammogram. So now, using this chart or this tree diagram, let's figure out the probability a randomly selected woman from this population tests positive for breast cancer in a mammogram. So, using our conditional probability model, we are looking for the probability that a human in this population has breast cancer from a positive mammogram result. So we know this to be true. What is the likelihood of this happening? So that is the intersection of both things. So the probability of having breast cancer and a positive mammogram divided by the probability of A happening, or just the positive mammogram happening. Now, what ends up happening here is that I'm looking for has breast cancer, so 0.01, and then from a positive mammogram, 0.97. And then I'm looking for all the possible ways or all the probabilities of which you can get a positive mammogram. So that happens 2 times in the last little branches of our tree here. So we get a positive mammogram from the same thing on the top, so 0.1 times 0.97, and we add it to the positive mammogram results with 0.99 times 0.06. So all of that works out to be about 14%. All right, that's going to do it for this video. Thanks for watching.